Now for that one, I didn't grab the lecture on my screen, so I'm going to try showing it here. We're going to talk about Bayesian psychometric model fit methods, right? Because at the end of homework 5, I asked you to check model fit. And it turns out in this lecture, we're going to talk about whether our model fits the data. We're going to talk about the same methods we learned in the linear models. PPMC for absolute model fit. Remember, PPMC stands for posterior predictive model checking. LOO, which is leave one out, and WAIC, Watanabe Akaike information criterion. Those are comparative for relative model fit. Both of those are tell us different stories. Like absolute model fit, that's important in psychometrics, but we'll get into that. We're still using our conspiracy theories. Our model set up today will be the graded response model. We're going to talk about it a little bit as well. And we are going to compare a unidimensional model for our data with a two-dimensional model for our data, right? See, there's a thought, a method to the madness here. I had this thought. Let's put these two together, right? Now we probably know what the result will be here, but let's take a look. Do you remember how to build PPMC back from October when we talked about it with respect to linear models? Let's talk a little bit about that. PPMC back then, what did we do? We, at every iteration in the chain, we took our model parameters and we treated them as if they were the true value in a population model, and we simulated data from those parameters with those parameters. So basically, we took our model. If we said that y followed a normal distribution, the mean of which was our linear predictor, then there was a residual variance or standard deviation. So basically, we plugged in all the values of our parameters for the linear predictor and the residual standard deviation, used the normal distribution to generate a point of data for each person, and then took summaries of that data to say whether or not our actual data look like what our model produced data was giving us. Do you remember that process? Very tedious, but helpful. So the same thing's going to happen in psychometric models. Psychometric models, we can use posterior predictive model checks to see how well they fit the data, absolutely. But in a psychometric sense, unlike in the linear models, things are a bit more complicated for what we have to generate, right? In October, we had one outcome, we had one Y. So we just generated a bunch of single Ys and summarized its distribution, right? Here's where the mean of Y happened to be. Here's where the standard deviation of Y happened to be. Now, in our example, we don't have one Y, we have 10. So instead of generating means and standard deviations for Ys, we may also have a covariance or correlation matrix for all pairs of Y, all pairs of items. And that's the key in model fit for psychometrics, is that model fit, a psychometric model implies a certain mean and a certain covariance matrix in your data. And it's in the covariances where the model misfit tends to happen. Most of our psychometric models recover our item means quite well and our item standard deviations, if we have those, quite well. But where we see model misfit is in how well a model describes the correlation between a pair of observed items. Oftentimes, a model might think that's too big or too small, and that's indicating to us that something else is missing from the analysis itself, whether we misspecified a Q matrix or whether there's some other dependency in the data that we're not recognizing. All of that's important information. And in a frequentist setup, if you've taken like Lisa's SEM class, or if you've looked at my slides, I use Lavon and R. When you run Lavon, the first thing you see is a table of model fit statistics, right? And you see things like RMSEA, root mean squared error of approximation, and CFI or TLI. These are indices to see whether your model fits. There's one on there called standardized root mean squared residual. Have you seen that? SMRMR, right? Yes, that's how I call it. Um, that one is the sort of the residual correlation, sort of the average residual correlation, right? Unsigned. Um, that's an absolute fit statistic. That's what sort of what PPMC is doing here. So that's the setup. We're still, for each iteration of the chain, we're going to generate data for every item. Basically, remember our data matrix here. We have 177 people and 10 items, right? So we are going to, in every iteration of the chain, create 177 by 10 data matrices, right? And from those data matrices, we can calculate summary statistics that we will use to compare our statistics from our data with, right? Our observed statistics. So those summary statistics are effectively, we could come up with univariate measures, which aren't very useful. An item mean, we could even come up with a chi-square. So our data are categorical, right? We have 1, 2, 3, 4, 5. We've observed in our data. We may have 1, 2, 3, 4, 5 we simulated. That's a observed by simulated box. We could come up with a chi-square for it, which is helpful. Although I will say in a Bayesian sense, this chi-square may not follow a chi-square distribution exactly. So like a frequentist p-value may not be as useful here. But the bigger the chi-square we know, the more misfit there happens to be. The smaller it is, the less misfit there happens to be. Um, I will say that these statistics aren't super useful in most cases unless you have really informative priors, and I say obscenely informative priors. Priors that are like, oh yeah, prior or something like that. I don't know, obscene. Um, you can imagine what's happening if you put a prior distribution that's too strong on like item thresholds. Your item mean is going to be shifted by it, right? It's going to move things away from where the data happen to be. There are also maybe cross-item constraints on all parameters, right? So there are models where we keep our loadings equal across all the items, the Roche model or the one parameter model, for instance, tau equivalent or parallel items models. Those will also have show up misfit and univariate measures as well, right? So we don't necessarily discard them, but for most of our cases of use, they're not going to be helpful. Uh, we also have bivariate measures. Now, these are where the things help a lot, right? What's a bivariate measure? It's basically a statistic describing a distribution between two variables, two observed variables, right? So for binary data, actually, let's think of it this way. If we had used a CFA model and treated our data as continuous, this would just be a Pearson correlation we could calculate, right? We have 177 people, 10 observations. We get a 10 by 10 correlation matrix from every simulated data set, right? Pearson correlation. For our data, though, it's polytomous data, and Pearson correlations are not great in polytomous data. They're especially bad for binary data, and that's because what happens to a Pearson correlation if you have a bound in your data? Turns out the range of correlation is no longer -1 to 1 unless there are certain conditions met, meaning that marginal item proportions are equal to zero point 0.5 and so forth, right? So we switch over to something called the tetrachoric correlation. Tetrachoric correlation is sort of the correlation between underlying continuous variables, if we were to assume that to be underneath the data. So for binary variables, we call it tetrachoric because what we think about is when we have two variables that are zeros and ones, if we envisioned an underlying continuous variable underneath each, then the binary variables that correspond to it were formed by cutting each continuous variable with a line. And when you cut each continuous variable with a line, you get kind of a four quadrants. And that's where the word tetra comes from. Those four quadrants, tetra being, was it Latin, something, I don't know, four? I don't know. Don't ask me. Polytomous data, the tetrachoric extension is something called a polychoric correlation. It's the same idea. All right. There are a few problems with PPMC. There's no standardized way to tell which statistics to use. I like the tetrachoric and Pearson correlations personally. Well, tetrachoric correlations for binary, polychoric for polytomous, and Pearson for continuous. Uh, there's also no uniform standard by which data should fit absolutely, right? So how many misfitting item pairs is too many? We don't know. Um, there, one of our former graduate students and currently assistant professor at University of Arkansas, Jihang Zhang, has some work. He had a nice paper in SEM talking about how to do PPMC with M2 statistics. And actually, that was this paper was one. He's got another paper he's trying to publish with his dissertation for it. There's no way to determine if a model is over parameterized, though, or it's too complicated. That's the other problem with PPMC. So basically, if your model doesn't fit, one of the remedies is to make it more complicated. Add a one in the Q matrix if items correlations aren't measured well. Well, we can keep doing that, and PPMC will keep getting better and better and better, but we don't know if that's over parameterizing our model, which is another problem we might have. And there's nothing in PPMC that sort of penalize model fit by model complexity. Right? That's actually where the information criteria and relative model fit makes a big difference. So PPMC is a important feature. We need to show model fit for PPMC in an absolute sense, but it can only go so far, right? We also need a relative sense as well. So if we wanted to implement this in stand code, here's how we do it for one theta, right? And remember, in generated quantities is where we do all of this work. Because to generate a data set with the parameters that we have, we need to take our model values, use a random number generator, and come up with a simulated data set here. Here I'm creating a simulated data set called SimY. It's an array, it's an integer value, number of items by number of observations. So it's a 10 by 177 array. And that's only because of this. In an array, the leading dimension is anyway. Never mind. It's row major. It's row major is what it's called. So I loop over items and observations, and for each part of that 177 or 10 by 177, I fill in using this ordered logistic random number generator. This is the cool thing about Stan also. Remember, ordered logistic was the distribution we used for the greater response model. Turns out there's an ordered logistic RNG, which will turn that distribution into something that generates a data for you. And here in our model, we just give it lambda. Now we only have one theta, so it's a vector. There's one lambda per item times our latent variable theta for each person, along with our set of thresholds for that item. And in generated quantities, lambdas, thetas, and thresholds are all the current values in the chain from that iteration, right? From the sampling process itself. So this is very similar to what you saw back in October with the linear model. The only difference being now we have to loop over each of our items, but at the end of this process, we have this data matrix that we can calculate statistics for. But rather than we have Stan calculate statistics, we're going to do that in R, and I'll show you that in just a bit, mainly because to get a tetrachoric correlation or a polychoric correlation, there aren't functions in Stan for those, so we have to do that on our own. For two thetas, it looks very similar, right? In fact, if you remember my code before, this is the code I used to estimate the multidimensional model with ordered logistic. Now it's ordered logistic RNG, but what goes into ordered logistic RNG is literally the same values that I put into ordered logistic in the chain itself. So Stan makes it a lot easier to go and generate data because it's essentially the same call you're doing for your observed data model. How are we doing on all this? Okay. So now here comes the fun part. Once I run Stan and I get everything out of Stan, I want to go and process it myself in R. And I'm going to show you, walk through my code on how to do that. Okay. So here I'm creating an object called SimData that has my modeled order logistic draws matrix. Actually, let's do this. Just a moment, please. I want to go to this code in my R instance itself, because I want to walk you through what I've got here. And instead of running it all from scratch, I will load my environment from before. So this is my stand code here. Now, here is my setting at PPMC. So here I'm grabbing from my two-dimensional model my simulated data. I'm taking it as a draws matrix. So I'm dwelling on this a bit because I don't think I've had you really look at that Markov chain much before. But what I'm getting from Stan is all of the posterior draws of the data for SimY. SimY being a data set for each draw itself. This is going to be a very massive matrix. And of course, here, oh, darn it. So here you can see it's 8,000 by 1,770. What is all that about? I had each four chains with 2,000 draws at the end of the posterior, and I had 177 people times 10 items each. The column names are like this right here. So what does this represent? The first column are all the draws for observation for item one for observation one. So person one's data right here for item one. That's all the values that we've sampled for them. Okay. So now what we're going to do is we're going to set up an object to store each iteration's PPMC data. Okay. So here, what we want to come up with is for each correlation possible, right? So now we have 107, we have 10 items. 10 choose 2 tells us we have 45 correlations. So we're going to calculate PPMCs for 45 iterations. What we're doing here is coming up with which correlation is going to show up of the four in the 45, right? So this loop right here is simply looping through all possible pairings of items and labeling what we're going to find. So our object at the end will have an item two, item one column to it. That'll be the correlation between item one and item two in our simulated data from the posterior predictive model check. Okay. And then the same thing for all other 45. And so now I'm going to, for each, I'm going to create a list object. And our list object allows us to create a spot to contain the correlations and a spot to contain the mean. So basically, I'm going to calculate each item's sample mean distribution and each item's sample correlation distribution. And now, and when I loop over each row of sim data, remember a row in this is each iteration's sample values. I then create a data frame. So if I say sample equals 1, I have my sample data frame. This is what I'm going to fill in with the data from Stan that was generated. This loop right here figures out where those data are and fills in sample data. So sample data now looks like a data matrix, like we would have observed, right? But this is simulated from Stan. Then I just calculate statistics to it. Here, I'm actually calculating the mean. This is our simulated data mean for that iteration. I'm not actually calculating tetrachoric, but here's the Pearson correlation for each as well, too. The correlation for each pair of items. Now, the names of each of these items are here in pair names, right? But here's our simulated correlation amongst all the items. So if I do this over and over and over again, and I know I'm about out of time for today, what I will come up with is a density of each of these statistics, a density for the mean, a density for each correlation. And that's what we use to compare our observed data with. And here, it's going to just going to continue in perpetuity because we're out of time for today. So on that note, I'm going to stop. Wait, hold on. Give me just 1 second. Here's our density of the item mean for item 1. That's where our observed mean is. That looks like it fits, right? PPMC. This is our density for the Pearson correlation for item 1 versus item 2. That's where the correlation where item 1 and item 2 is. Does that look like it's in the middle? It's a little on the side, but it's not in the tail. We'll come up with the posterior predicted p-value next time. All right, that's where I'll stop. Thank you for your time today. Thanks for being here. I have office hours tomorrow. I will hopefully, health willing, have class Thursday, and we will continue this lecture Thursday and then get into the remaining lectures that we have then. And if we have to spill over past Thanksgiving, the fall break next week, we'll do that in the week afterwards. So great to see you. Thanks for being here. Hope you have a great day. Take care.